Hello, so this is the last problem from the first problem set of David Tong's lecture notes. So it deals with this action here, and we're doing these transformations, these scale transformations. So we scale our coordinates by lambda and our fields by lambda to the minus d. And if we do that, so I just wrote here how the derivatives, how our d mu and our d mu's change. So they will change, we'll just get a lambda to the -1 for each of them. And we're asked to show, or we're asked under what conditions is our action invariant under these transformations. And so that's why I needed to know how our derivatives transformed. And another note here is that, so our scaling transformation looks like this. So the matrix of that transformation will have just diagonals all of lambda. And so the determinant of that transformation matrix, or the Jacobian, is lambda to the 4th power. And so our volume element will be lambda to the 4th times our original volume element. So if we use all these rules for our for the changes in our coordinates and fields and derivatives, we get this. And so and we just want this to be invariant, so we need all of these lambdas to go away. And so for the first term, just this derivative term, we have in total, if we combine all our lambdas, we will have lambda to the 4 minus 1 minus d minus 1 minus d. And for our term to be invariant, we need lambda to that power to be 1. So in other words, we need this exponent to be equal to 0. And for that to happen, we need d to be equal to 1. So that's for this first term. So if d is 1, has to be 1, then our second term here will have a lambda to the -2, and then after multiplying by this lambda to the 4th, it'll have a lambda squared. So there's no way to make this term invariant unless m is just equal to 0. Then it won't matter what lambda is. So we have to have m equal 0, otherwise our action can't be invariant. And then lastly, we have this term. And so if we want it to be invariant, we'll be led to the condition lambda to the 4 minus pd is 1. And since we know d has to be 1, then that's just 4 minus p equals 0, so p equals 4. So those are our conditions. And then it asks how things generalize in n+1 dimensions. But basically, the only thing that changes is our Jacobian will get another factor of lambda. So if we write, instead of d for x, we would write d n+1 x, and correspondingly we'd get a factor of lambda to the n+1. So basically we can just define the general conditions. We can just replace our 4 here with n+1 and solve for our parameters as a function of n. So if we do that, our new condition becomes that d should be n-1/2, And then this condition becomes 4 minus p times n minus 1 over, nope, sorry. We just plug our expression for d as a function of n in here and replace 4 by n plus 1. And that will lead to the condition that p should be 2 times n plus 1 over n minus 1. So then it asks for us to find the conserved current corresponding to this transformation. So to do that, okay, so it'll be basically this looking thing, only I've forgotten to write minus RF mu. So how do we do that? So we need to write our transformations infinitesimally in order to find our conserved current. So we can just write lambda as 1 plus epsilon, where epsilon is very small. And then our field will transform like this. So the inverse of lambda in this case will be 1 minus epsilon. And so we'll have, so our phi will become this. And then I can distribute both, so I'll have two terms when I distribute into this 1 minus epsilon. So it'll look like this. Then we can use our usual chain rule to expand both of these terms. I'll end up with 4 terms that look like this. And this term is quadratic in epsilon, so it's very small, so we throw that away. And then we can kind of just read off that delta phi here will just be minus x mu d mu phi minus phi. And then we can note that the Lagrangian changes like this. So we saw before, so the action, in order for it to be invariant, we got this lambda to the 4 from our volume element. And so that means our Lagrangian picked up a lambda to the minus 4 to compensate for that. So that's why we have this transformation rule. So it's very similar to this. So instead of 1 minus epsilon, we can Taylor expand this as 1 minus 4 epsilon. And so things work out the same way. We just get, 4s here in these two terms. And so that leads us to our change in the Lagrangian of this. And then we can rewrite this term. We can, do the integrate by parts thing, but not integrating. So this is equivalent to these two terms. So we're doing this because we need to write our change in the Lagrangian as a total derivative. So we can get our f mu. But so it's these two terms, and then this term, d mu x mu, we will just get 4. So these two terms will cancel, and we're just left with d mu of minus x mu L. So our f mu will be minus x mu times the Lagrangian density. And so then we can just write down our conserved current, which will just be dl. So dl d mu phi is just our normal. This is the derivative term is just the normal Klein-Gordon term. So that is just d mu phi upper. And then our delta phi was this. And minus f mu. So minus x mu L. So it's this.